Right, welcome back to Physics 30. This is the second video. So we talked about inertial frames a little bit and discussed that Newton's laws of motion hold true in any inertial frame. They may differ from each other, but they're both equally valid. Galilean Newtonian relativity involves certain unprovable assumptions that make sense from everyday experience. It assumes that the lengths of objects are the same in all reference frames. That seems reasonable, but as we'll see later on, that doesn't always happen. And time passes at the same rate in different inertial frames. And again, we'll see that there are some things that need to be adjusted for that. In classical mechanics, then space and time are considered to be absolute, unchanging. Their measurement does not change from one reference frame to another. The mass of an object, as well as all forces, are assumed to be unchanged by a change in inertial frames. That the laws of mechanics are the same in all inertial frames implies that no one inertial frame is special or better. We express this important conclusion by saying that all inertial reference frames are equivalent, with the key parts inertial frames. For description of mechanical phenomena, no one inertial frame is any better than the other. A reference frame fixed to a car or an aircraft traveling at a constant velocity is as good as one fixed to the earth. When you travel smoothly at constant velocity in a car or airplane, it's just as valid to say that you are the one at rest and the earth is moving away. So if you remember being a little kid traveling in a car, so here's a car here, ooh, that's a wacky looking car, it looks futuristic. So you're sitting in the car, and of course, someone on the street would say, oh, you're moving to the right. But if you're looking out the window kind of in a daze, you see the earth and everything moving behind you, and you could say that you are at rest and the earth is moving in the opposite direction, and that would be equally valid, provided that you're going at constant v. So it's equally valid to say you're at rest and everything is moving away from you. And guess what? There is no experimental evidence or experiment that you can do to tell which frame is really moving. There's no way to single one reference frame as being moving or at rest. Because if you think about it, if you're just at rest in a classroom, you drop a ball, you throw a ball in the air, you catch it, etc. All observations you would make would be equivalent to if you were inside of a van or a vehicle that had no windows and it was moving at constant v. All of those experiments, you would get the same result. Balls fall to the ground right below you. Throw a ball up in the air, you catch it, no problem. So there'd be no way to distinguish between these two because you get the same results. And if you think about it, when you were doing things at rest and see experimental results, we're on Earth and we are actually moving. And for our intent and purpose, we could say constant velocity. So we do get the same results, which is very interesting. Now, so this is all fine and dandy. It makes sense. Complication arose, however, in the last half of the 19th century. Maxwell's comprehensive and successful theory of electromagnetism predicted that light is an electromagnetic wave. Now, sometimes. Maxwell's equations gave rise to the value of c, the speed of light, as being this. And this is just what it was measured to be. Now, here's the thing. The question arose, in what reference frame is the speed of light that value? So it is assumed that light would have a different speed in different reference frames. So thinking about the very first thing we talked about, the train example, and that's why I talk about this. Because this person here, if we know that light travels 3 times 10 to the 8 meters per second, and let's say this guy had a flashlight and flashed the light. So if we were going 80 kilometers per hour and this guy flashed a light, this guy you'd think would say, well, the light is traveling 3 times 10 to the 8 plus the 80 kilometers per hour, and that's how fast light would be traveling. But unfortunately, that is not correct. Or if we were moving away from a light source, let's say here's the sun, and we're moving in a rocket ship this way, and so we would say that the light that reaches the people in here would be 3 times 10 to the 8 minus the speed that we're moving. So light is, because we're moving away from it, so light is catching up to us. So light would appear to be moving at this speed. But guess what? That doesn't happen either. So Maxwell's equation had no provision for relative velocity. They predicted that the speed of light is just simply 3 times 10 to the 8. Now, it seems to be that, well, in what reference frame is this in? And strange as it may seem, experiments have detected that there's no difference for the speed of light in any reference frame. The speed of light is just simply this, 3 times 10 to the 8 meters per second. A number of explanations were put forth over years, but they led to contradictions and weren't accepted. This null result was one of the great puzzles at the end of the century. So no matter, even if you're on a train or off the train, you would still say that the speed of light is that number. There's no adding, there's no subtracting. It's just simply this value in air or in a vacuum. Then in 1905, Albert Einstein proposed a radical new theory that reconciled these many problems in a simple way. But at the same time, it completely changed our ideas of space and time. So that brings us to postulates of the special theory of relativity. Einstein was motivated by certain questions regarding electromagnetic theory and light waves. For example, he asked himself, what would I see if I rode a light beam? And the answer was that instead of traveling electromagnetic wave, he would see alternating electric and magnetic fields at rest whose magnitude changed in space but did not change in time. Such fields, he realized, had never been detected and indeed were not consistent with Maxwell's electromagnetic theory. He argued, therefore, that it is unreasonable to think that the speed of light relative to any observer could be reduced to 0 or be reduced at all. This idea became the second postulate of the special theory of relativity. In his famous 1905 paper, Einstein made a proposal that embodied 2 postulates. The first was an extension of Galilean Newtonian relativity principle to include not only the laws of mechanics, but also those at rest in physics. Now let's take a look. So these are 2 key things. So the first postulate, which is sometimes called the relativity principle, is that the laws of physics have the same form in all inertial reference frames. So if we're at rest or moving at constant velocity, Newton's law holds. Physics holds. So the first postulate can be stated as also there's no experiment that you can do in an inertial frame to validate whether you are at rest or moving at constant velocity. There's no experiment you can do. Second postulate is referred to as what we just talked about, the constancy of the speed of light. So light moves through empty space. So when we're talking about light speed, we're talking about moving in empty space, out in space, a vacuum, etc. Because we know light slows down when it goes through a medium, right? From physical science 20, if light goes through glass, it slows down. But we're talking about light just going through a vacuum, through space. So it goes through empty space with a definite speed, which we call little c, which is 3.00 times 10 to the 8 meters per second, independent of an observer. So whether it's on a car or away from a car, it is that number measured by everyone. So these 2 postulates form the foundation of Einstein's special theory of relativity. And it's called special to distinguish it from general, which is later on, in which we talk about non-inertial frames. So in MP1.1, we talk about non-inertial frames and the funky things that happen with that. Special theory, which is what we'll discuss here, deals with inertial frames. So frames that are not moving or ones that are moving at constant velocity. Now the first postulate is simple, right? All inertial frames are valid for physics. That second one, though, is hard. It seems to violate common sense. First of all, we have to think of light traveling through empty space. The second postulate also tells us that the speed is always the same for light. No matter if the speed of the observer is moving or if the source is moving or not moving, it does slow down in different media, like I mentioned, but in a vacuum, it doesn't change. Thus, a person traveling toward or away from light will measure it as 3 times 10 to the 8 meters per second. no matter what. So even if you're traveling with the light or against the light or sideways from the light, it is always going to be that speed. And that is a conflict with our thinking. This conflicts with our everyday experiment. We would expect for it to have an additive part, right? If it's going with a spaceship in one direction, and if we're from another spaceship watching it, we would think that you need to add the spaceship's value onto the speed of light to get the speed of light. But guess what? That doesn't happen. So that's an interesting part, that second piece, that second postulate. So we would expect it to add on, but it doesn't. All right, we'll see you again.